Hello, guys. Good day to you all. Welcome to the second episode of this series, Thermo261 in 7 minutes with McDaniel. During the last class, we were able to have a conversation about the energy equation of the first law analysis, where we come to understand that Q is equals to mu, that is m change in U plus work done. And we talked about the analytical questions you need to ask your question paper before answering the question, and so that you need to understand the type of system, the behavior of the working fluid, the type of process, and knowing whether if you should neglect the potential energy effect or the kinetic energy effect. And we say that for the exam purposes, the E261 question paper is divided into 5 major parts, which are closed system ideal gases, closed system water properties using property table. The third one is open system ideal gases. The fourth one is open system water properties, where we use property table. And the fifth one is thermodynamic cycles, where we talk about power cycles, refrigeration cycle, and Carnot heat engine. We talked about this during the last episode. And for this particular episode, I'll be focusing on the first part, which is closed systems ideal gas. I will be solving some questions regards to that. So once again, welcome to ME261 in 7 minutes with McDaniel. Here we'll try to analyze thermodynamics to its simplest form. Here is the midterm text exam of last year, number 2. If you check number 1 question, it's not ideal gas. So for now, we are focusing only on the ideal gas questions. If you look at that question and trying to make assumptions for the question, I believe I've taught people how to formulate these assumptions. The system is a closed system, so we're going to use Q equals to W plus M change in U. I believe you know the difference between closed system energy equation and open system energy equation. Then looking at that question, the working fluid behaves ideally. Please, you can pause this video and get your midterm test exam question. There is midterm exam question last year, number 2. If you look at the working fluid of that question, it behaves ideally. So we are not using property table. And since it behaves ideally, the temperature is going to be in what? Kelvin. Then the process is polytropic. And for polytropic process, there are 2 major equations, which I stated here. Go back to my previous video. I showed you people all the work done equation for all the processes. Then since it's a closed system, we're going to neglect the PE and KE effects. I explained this during the last video. Now, looking at that question, after you have done your assumptions, assumptions will guide you on how to solve the question. Now, you will now state down your given. For the particular question, it is a one process. And since it is a one process, 2 states make up one process. If it's a 2 process, 3 states make up what? 2 process. If it's a 3 process, 4 states makes up a 3 process. But since this one is a one process question, we are expecting 2 states. So for state 1, P1 is not given, T1 is not given. Mass is given as 2 kg. Why do I write M1 is equals to M2, which is equals to 2 kg? For thermodynamics, we expect that the mass is conserved. So the mass in state 1 is same thing as mass in state 2. So based on the question, you should ask yourself, what is required of me in this question? The first thing that was required from us is to calculate P1, to calculate T1, to calculate change in energy, change in internal energy in kilojoule. Please note the difference between calculating change in energy in kilojoule and calculating energy change in energy in kilojoule per kilogram. In kilojoule per kilogram, we are talking about the intensive property. but in kilojoule, we're talking about the extensive property. Then they also asked us to calculate um, heat in kilojoule per kilogram. And based on the fact that this question is a closed system, Q will be equals to m change in U plus W, where change in U is already given as MC VT2 minus T1. Then we now go over to the calculation. We already know that the question is a polytropic um, process, and we have two formulas for polytropic. But if you look at the parameters given, you see that the equation 1 will leave us with two unknown parameters. So we can't work with that. So we'll go over to equation 2 since we know all the parameters except T1. So now fixing in the value for the work, which was given, mass, which was given as 2, R, which was 0.287, T2 equals to this, T1 equals to this, 1 minus N, and they gave us N to be 2. When we calculate, we will make our T subject of the formula, and that will leave us with this. Remember, we always convert our temperature to Kelvin, but for when the working fluid does not behave ideally, we're not converting temperature to Kelvin. Then now that gave us that T is equals to 883.7 Kelvin. Now we have found our T1. Okay. In order for us to find our P1, there is a polytropic equation that relates all the properties in a polytropic process. Check my previous video, I talked about all those things. So for polytropic, for the temperature pressure relationship, this is the formula. Okay, then fixing in by substituting the values, we have that 434.7 over 883.7 is equals to 5 over p raised to the power half. And when you make p the subject formula, p will give us 20.66 bar. So I've already calculated for our P1 and our T1. Then for our change in U, you can see that if you substitute M, which is 2, CV, which is 0.718, T2, which was given, and T1, which we have calculated, you see that our change in internal energy will be minus 644.7 kilojoule. Then moving over to the heat, when we fixed in all this value plus W. Remember, that's why we want to check whether if it's a closed system or not. For closed system, this is the formula. If it's an open system, I believe you know, I have explained to you people the formula for open system. But since it's a closed system, that's why we're using this to calculate our Q. Our Q was gotten as minus 386.98 kilojoule. And this negative tells us that heat was rejected to the surrounding. If you want to state that, you say that 386.9 kilojoule heat was rejected to the surrounding. Please don't say minus 386.98 kilojoule was rejected to the surrounding. Once you put this minus, you're already telling us that heat was rejected. So let's look at the second question that gave us an insight of how this ideal gas in a closed system looks like. So for exam question number of last year, number 1, the assumption tells us that the system is a closed system. So we're using this energy equation. The working fluid behaves ideally, so we will not use property table, and the temperature will be in Kelvin. The third assumption tells us that the process is adiabatic polytropic. Once you hear that it is adiabatic, Q is equals to 0. And for adiabatic polytropic, it means that N is equals to K, which is equals to gamma. Please, whenever you hear that a process is adiabatic polytropic, it means that N is equals to K. Okay, But when it is only polytropic, without saying adiabatic, it has N is equals to a value greater than 1. And when it is only adiabatic, don't consider this, only consider q equals to 0. But once they say it is adiabatic polytropic, this is what this statement implies. Then the final assumption says neglect PE and KE effect. When I say PE, I mean potential energy. KE means kinetic energy effect. So we'll go over to the given. For state 1, we found out that P1 is equals to 1.035 bar, which is approximately 103.5 kilopascal. T1 is equals to 21 degrees centigrade, and we'll convert to Kelvin. And specific volume, please remember, volume is different from specific volume. Volume is an extensive property, and its SI unit is what? A meter cube. But all extensive properties are expressed as per unit kg. So this our specific volume is given as 0.75 meter cube per kilogram. The state 2, we don't know our pressure, our temperature was given, and they gave us a volume ratio, which is V1 over V2 equals to 6. And they gave us comprehensive work input, which is equals to 7.4 kilojoule. They asked us to find, that is the required, R, CV, CP. CV means specific heat capacity at constant volume. CP means specific heat capacity at constant pressure, and M is mass. So for the calculation, from ideal gas law, we know that pressure times specific heat capacity is equals to this, because specific heat capacity means volume over what? M. So now recall that PV is equals to MV MRT, which implies that PV over M is equals to RT. So V over M, which is the specific volume, is represented with this italic V. Now, making R the subject of the formula for this particular equation, we now have R is equals to P specific volume over T1. And when we impute it, we'll get this. Please remember, when doing this calculation, convert your pressure to kilopascal. And how do we convert it to kilopascal? By multiplying it with 100. And we'll get our R to be this. Then we now calculate our specific heat capacity. But you see that our specific heat capacity relates to this R based on the ratio of specific heat. Okay? So this ratio of specific heat capacity, which is gamma, is expressed as Cp over Cv. But we know that T2 over T1 is equals to V1 over V2 raised to power gamma minus 1. This is polytropically. Okay? So gamma minus 1, by the time you take the logarithm of both sides here, sorry, I'm having a little kata. When you take the logarithm of both sides here, you see that this exponential will come down, and you now divide logarithm of T2 over T1 by logarithm of V1 over T2. Please, V2, please, if you don't understand this, ask me in the comment section, and that will help you explain. So by the time you input all these things and solve, you see that gamma minus 1 is equals to 0.388. So now, making gamma the subject formula, you add 1 to it, and if you add 1 to it, gamma becomes 1.388. Now, for us to get our specific heat capacity, at constant volume is given as this, R all over gamma minus 1. And when you impute that, you get 0.68 kilojoule per kilogram Kelvin. When you want to get your Cp, which is specific heat capacity at constant pressure, you now see that Cp is equals to gamma times Cv. The Cv we got here, we multiply it with gamma. we got our gamma as 1.388. Times it with CV, we get 0.944. Then for your mass, you substitute mass from the work done equation. And when you hello, so the work done equation for um the work done equation for an adiabatic polytropic equation is given as this, because work done is equals to mc v t2 minus t1 plus, that is, you plus it to q, but q is already 0. Do you understand? So that now gives us with this equation. M will now be, if you make M the subject formula, we get this. Then M will now be equals to 0.0369 kilogram. The last example I'm going to solve here is a question from the year 2015, number 1. So if you go over to this so I would advise you to go to pause this video and get your past question for 2015. If you get your past question for 2015, you can pause this video if you don't have it, to make a screenshot of this past question. Thanks to my wife, she decided to pen this down for you guys to have a view of it. So this is the question, and from that question we can see that based on the assumption the system is a closed system. The system is a closed system. The working fluid behaves ideally, and there are two processes involved. The first process is constant volume. For every constant volume, work done is 0. The next one is polytropic work done. We already know the formulas for polytropic work done. Having said that, the last assumption is that neglect potential energy and kinetic energy effects. Then from the question, it was given that for state 1, P1 is equals to 3.4 bar, 3.45 bar, V1 must be equals to V2 because it's a constant volume. And remember, we said that there are two processes involved. And remember what I said from the beginning of this video, that once you have a two process, 3 states makes up 2 process. So we're expecting 3 states properties here. So for the second state, P2 is equals to 0.69 bar and V2 is equals to V1. And for state 3 is a polytropic. From state 2 to state 3 is a polytropic process with N equals to 1.3. Therefore, P3 is equals to 3.5 bar, V3 is equal to 0.283 meter cube. They require us to find the total work done. And for you to find the total work done is W1 plus W2, W12 plus W23, where W12 is already equals to 0 because of constant volume. W23 is given by this formula. We convert, remember, the reason why we add times 10 raised to power 2 is for us to convert meter cube bar to kilojoule. Okay, hence if we impute P3, V3, P2, V2 and N into this equation, we are going to get W23. But remember, they did not give us V2. So from polytropic relationship, V2 is equals to V3, P3 over P2 over 1 over N. And when you impute that, you will get V2 to be this. Therefore, W23 will be given as this. This implies that our W total will be equals to W12 plus W23, and W12 is already 0, and W23 is equals to this. When you add the two together, it's going to give you 101.43 kilojoule work done, total work done. Thank you very much for your time. I also want you to see this product called Pepsodent Charcoal. It's very, very good. It's a natural charcoal whitening toothpaste. It will go a long way to help you make your teeth strong. And If you are the type that sweats a lot, you can use Rexona body spray or Rexona um, deodorant. The Rexona comes in different variants. You can use them. It comes in different variants, and this will be very good for you. Thank you very much, and success at your exams. In my next video, I'll be teaching on closed system water substances, where we're going to use property table. Thank you.